So, but if you're actually, but I mean, that was our model when I comes up, that's.
Huovinen. H. Yeah. Yeah.
But if you want to move it.
Okay, so now I just click and change the.
Your.
It's
Yeah, you're right.
point it comes.
Right at the front, you get 3+ empiric C goes with a 3+ in chromite easily. But as that front's moving around, what's moving that chrome is the fluid. And so therefore, in the fluid, it not only would have to be a 2+.
So it has to be reduced enough to have.
Yeah.
Which, I mean, is that likely? I just, because chromium 2+ is not a common oxidation state and under.
Let's keep the discussion for like start. So now we have a pleasure to invite Huovinen to talk about the Kemi.
Thank you. Okay, so my topic is constraints on the textural and chemical variation of chromium oxides in the ore bodies of the Kemi intrusion. So we started this mineralogical study in 2021 in GTK, and it's related to the Outokumpu mines because they are expanding the mining to the new areas all the way to the 1 kilometer depth. And the main questions were related to the mining process, is the sources of iron, and of course the composition of chromites and other oxides. So the results were so interesting that we asked a permission to continue this study. So now we have this very, very good cooperation with the Outokumpu chrome mine and GTK and the University of Oulu. So, and we have a permission from Outokumpu to present these results for you. So the Kemi chrome mine started in 1968, and it's nowadays the 5th biggest chromium producer in the world, and also the biggest, the only one in the EU. And the ore is low grade, but from the very beginning, the Outokumpu decided to concentrate on ferrochrome production. So the ferrochrome plant started to operate at the same time as the mine. A little bit about the geology. So Kemi layered intrusions belongs to a big group of these early Paleoproterozoic layered intrusions in Finland and in Russia. And it's quite typical. You can, the lower part of the intrusion is ultramafic with periodic rocks, and then we go to the pyroxenic rocks, and the upper part is composed of caproid cumulates. The silicate minerals are strongly altered, and you are going to see them, especially in the lower part where we have the ore. We have the same problems as in Jakuri. We have the intrusion is 15 kilometers long, and the thickness is less than 2 kilometers, and the average thickness of the main chromitite is 40 meters, but it can be over 100 meters in places. A close-up. So there's one profile drilled through the whole intrusion, and from the basement 90 meters above that is the main chromitite layer. There's also around 8 other layers in the lower portion of the intrusion. The upper contact is erosional, and it's covered by this early Proterozoic schist belt rocks. Then something about the ore bodies. So actually they all except this Nuottijärvi ore body, they represent the same main chromitite horizon, and they are divided by these faults, and they are treated as separate ore bodies, but they are the same. And in the western part, they are less altered, and the highest, they are most altered in the eastern part. The rock type classification used here is the same they use in the mine. So it's based on the Gangu minerals in the rocks. Okay, so this is the actual ore here. So we have studied these 10 real cores. They are now in this same picture, but they are actually from the different levels. And here you can see the Nuottijärvi ore body. It's above the main chromitite horizon. Okay, so now we go to we have to look at the silicates. Not much primary things here today, sorry about that. So in the left, you can see the least altered rocks, believe it or not. So we have serpentinites, serpentines, chlorite, tremolite, and it's followed. In the middle, you can start to see some talc, and then we are going to get more calcite there and more talc with that. And this is the final state, the talc carbonate altered rocks, and this is the most common rock types we can see, the talc carbonate rocks and serpentin-based rocks. But these are the first primary olivine and clinopyroxenites assays we got from the lower part of the intrusion. So you can see that the phosphorite content in olivine is over 90%, so it's a bit higher than in the previous studies. Also, and here you can see the difference in Surmaja, it's from the main chromitite horizon, and this Nuottijärvi is from the upper chromitite layer. Then I think I skipped this. We have serpentines, and you can see some differences between the serpentines from olivine and from pyroxenites. Then we have glaucopites, tremolites, clinochlor, talc chloride, plus calcite, magnesite, and talc. Magnesite is the most common carbonate mineral we have there, and that's about it. Then we go to chromites. So you can see here at one glance that we have two types of alteration here. So we have this blue one, which is the typical zoned type of alteration, which goes to the iron end of the chromite composition. And then we have this so-called porous type alteration, and it's related only to ore grade samples. So you have to have high oxide silicate ratio. All the magnetite is secondary. So now some nice pictures. So in the upper picture, we have this traditional textbook example of this zoned alteration, like and always with alteration, we decrease the magnesium and aluminum content. And there's also some changes, is, for example, in zinc. Here is titanium, manganese. In here we start to get this cross-cutting calcite veins. So this is the least altered sample with it's related to serpentinization. We get some extra magnetite and iron. It's precipitated around these chromites and silicates. So then we start to get these cross-cutting veins. So we can see in the height here that we have this calcite. We get extra magnetite. It cuts the overlying zoned textures, and also we disturb these rims with some of these trace elements. Here's a close-up. You can see nicely that this magnetite cross-cuts everything. So this is, of course, not nice for mine. Then we have this so-called porous alteration, or maybe it's X solution. It's related to these 111 crystal shapes in here. So we got sometimes more, we have loss of aluminum, magnesium, but we can get more chromium and a little bit more iron. This is only in ore grade samples. There's no clear connection to the host minerals. And we also have this rutile X solution here. So this is a close-up of this. So we have some silicates always. silicate inclusions. We have in this is tremolite chloride rock, rutile, and this alteration. This is chromium rich patches. This is really a close-up. We have a lot of this where we have this very fine lamella here. So you can see also we have similar silicates. We have this white is the chromium rich part. Aluminium starts to go here around those. And we have also rutile here. So they really have to be in the form in the same process. Then this is the last stage of the alteration. So these are related to dark carbonate altered rocks. We start to get actually here, you can see little titanium lamellas. And also we can precipitate this ilmenite together with magnetite in these fractures here. Yes, okay. So then the chromite composition of the ore, so the main point here. In left, you can see all the samples, or this is all data is microprobe data. So here you can see that if we have all samples here in orange and green, so we have this porous type alteration here. And when we have more disseminated samples, we start to get more iron here. But in here, if we take this altered stuff out as well as we can, and we have only ore samples here, so we can see that in serpentine paste ore we have the lowest chromium iron ratio, which is the most important factor to mine. And also typically we have the best grade samples are tremolite chloride samples, so probably they present olivine rocks primary and then pyroxenite rocks. And if you look at the ore bodies, so we had this in yellow, we have this Nuottijärvi, which was the younger and upper chromite. So we can see change in aluminium, chromium, and vanadium content, for example. And this red and green, they are the most altered ore bodies in the eastern side. So I think the composition is quite disturbed. They are talc carbonate altered rocks. That's it. Yeah. Thank you.
We have time for questions.
Thanks. This might be an ignorant question, but I'm going to ask it anyway. So do you think it's progressive, the alteration from the serpentine alteration to the talc carbonate and the other things? Do you think the serpentinite one is like the precursor, or do you think there's genuinely different fluid involved?
Maybe at first, yeah. I think that when we have separate events, so when you start to the serpentinization process, and then you go to the chloride, then you get amphibolites, then you got talc. That's one thing. And it's not so altered actually. But when you start to get the CO2, then it's the completely mess, and that's a different story. So yes. That's my idea.
So the talc carbonate step hasn't necessarily been a serpentinite. But
it's you can actually see that there are boundaries, quite clear boundaries. So it's comes from somewhere else. I don't know where it comes.
I have more questions, but I'm going to give this away next.
Yeah. Yes, let's speak later. Yes, there are. They are not systematically studied, but if we saw something bright and interesting, we check those. So often laurite, spherulite, but probably something later as well. But there are.
Just one more question, please.
No, thank you very much. Thank you.
Okay, so now please, Mr. Huber, talking about the magnetite. Now,
Is invited to, so.
Okay, can I navigate this?